Hello, this is Jack Jackson. In this video we're going to go over some review problems about integration, both on some concepts of integration, finding antiderivatives, and evaluating integrals, and applying them. This particular group of problems is a set of problems that I used for a practice exam one semester. So let's take a look here. The first question is, what is the definition of a definite integral? Well, in my class we're using this basic definition. Let delta x be b minus a over n, so delta x is going to be the width of one interval from a to b divided into n equal pieces. N is going to be the number of intervals or number of rectangles we look at. X sub k then becomes a plus k times delta x. That puts x sub k as the x value at the right side of each of these intervals, at the right side of each rectangle. Then when we come down here we do f of x sub k, which would be the height of the rectangle at the right end of the interval, times delta x, which is the width of the interval, and I guess technically I should say the height might be a signed height, a positive going up, a negative if it's going down, and then this becomes a signed area, either positive if it's going above the x-axis, negative if it's going down, but otherwise an area. And then that's the area of one rectangle. We add those up from k equals 1 to n. That becomes what we call a right Riemann sum. Then we take the limit as n goes to infinity, and now we have a definite integral. So here we have a table of values for a continuous function. Can we evaluate this at least approximately? And we want to do that. And notice that it asks us to use three intervals. So that's n. N equals 3. And then delta x then is b minus a over n. Well, I'm sorry, this should say 2 to 20. Need to fix that typo. From 2 to 20. And so this goes from 2 to 20, so a is 2, b is 20. 20 minus 2 is 18. Divide that by 3 equal pieces, we get a delta x of 6. So if we go 2 plus 6, that's 8, so there's one interval. And 8 plus 6 is 14, so there's our second interval. And then 14 plus 6 is 20, so there's our next interval. So those are the three intervals we're dividing this up into. Now, if we want to do left Riemann sums, what we do is we take the width of the interval, which is delta x, which is 6, and we were going to multiply that by the height for each rectangle and add those up. Now, since the 6 is the same for each one, we can factor that 6 out and just add the heights. Now, we're going to add the heights at the left end of each interval. So we're using, for this first interval, we're using 1.68 for the height. For the next interval, we use the 5.43, and the last interval we use 2.93. So we add those three things together, you get 10.04 times 6 is 60.24, and that is our left estimate. Okay, now for our right estimate, we want to do the same thing, except the difference is now that we're using the right end of each rectangle. So on this first interval, we're going to the right side here to find the height of 5.43. We go to the right side of the next one to get 2.93, and the right side of the third one to get negative 5.85. Add those together, that's 2.51 times the width of the interval, delta x is 6 each time, and that gives us 15.06 for the right Riemann sum. Now we can get a better estimate than the right or the left Riemann sum by averaging the two. And that gives us our trapezoid estimate, left plus right divided by 2. So that's the 60.24 plus 15.06, and then divide by 2 is 37.65. Another way to do it is by doing at the middle of the interval, and here we would use for the first interval, the middle of it is 5 for the x value, the corresponding y is 3.78, and for the second interval we use 6.21 for the height, and we use negative 1.29 for the y value. there on the last interval. Add those together, it's 8.7 times 6 for the delta x there, and that gives us a 52.2. We can get our best estimate yet, which is Simpson's rule, by averaging the midpoint and trapezoid rule estimates, but we do it by a weighted average. We do 2 times midpoint plus 1 trapezoid divided by 3. That's 47.35. Now I would call all of these, I would call this L sub 3, R sub 3, T sub 3, M sub 3, and S sub 3, although some books, in fact most books, would call this S sub 6, because they're thinking of this as actually 6 intervals instead of 3. I prefer to think of it as 3 intervals with the using information from the left, right, and the midpoint of that interval. Now, the next thing we're going to do is we're going to use we're going to do this same process, but we're going to take this function here from 2 to 14, integrate ln of x over x 11x to the 5th dx, and we're going to use this with 18 subdivisions, what I would call 18 subdivisions for all of these. Some books would call that 18 for the first 4 and 36 for the last one. And we can make a table with these actually 37 different values there, because we need to divide this into 18 intervals. This will give us 18 intervals, which each one has a left and a right endpoint in the middle, where we have to evaluate the function. Of course, some of those overlap. And this would give us a bunch of points to evaluate and work these out with the same rules that we just did above. But I also have a calculator program that does the same thing, and so if you see my earlier notes and put in this calculator program, you start by putting the function in y1 that you want to integrate, the integrand we call it. So ln of x divided by 11x to the 5th, don't forget the parentheses around the denominator there. And we want, and be sure you close parentheses on the logarithm as well. Okay. And then we run the program called integral, and it asks for a, which is our left endpoint, which is 2, b, which is the right endpoint, which is 14, and n, which is 18. And then it will produce left, right, trapezoid, midpoint, and Simpsons. So there's left, right, trapezoid, midpoint, and Simpsons. Be careful right here. So when you see that e negative 4, remember that means times 10 to the negative 4th. So that's actually move the decimal 4 places to the left. So that's 0.3 zeros and then the 807 whatever. And so when we work all that out, these are what we get for those different values. Of course, the Simpsons rule is our best estimate of those. All right, in the next one, we can compute this antiderivative. So it's asking for a family of antiderivatives here. And I want to think of this as an antiderivative. The sum is the sum of the antiderivatives. So 4x to the 5th, that's 4 times the antiderivative of x to the 5th. X to the negative 1 is 1 over x, so that's just 6 times the antiderivative of 1 over x dx. Then we got negative 2, we can think of the square root of x as x to the 1/2, but it's in the denominator, so we can think of that as x to the negative 1/2. And this is just a 7 times the integral of dx. So we can use our power rule here. The power goes up 1 to 6, divide by the new power. So you're dividing by 6 or multiplying by 1/6. 4 over 6 is 2/3. The antiderivative of 1 over x is log of the absolute value of x, or if I thought of it, the antiderivative of x negative 1, same thing, log of the absolute value of x. And then this is the normal power rule. This goes up 1, 1/2, negative 1/2 plus 1 is positive 1/2. Multiply by the reciprocal, which would be 2, times that negative 2 is negative 4 right here. The antiderivative of dx is just x, and then we always have plus c. You can check this by doing a derivative. 6 times 2/3, 6 divided by 3 is 2, times 2 is 4, and the power goes down to 5. That's the first term. The derivative of the absolute value of x is 1 over x, times 6 is 6 times x to the negative 1. 1/2 times negative 4 is negative 2. Power goes down 1. That's 1/2 minus 1 is negative 1/2 of the power, which is 1 over square root of x. and the derivative of 7x is just 7, the derivative of c is 0. Switching it back to something more like what it starts with, we rewrite the x to the 1/2 power as the square root of x. I can drop the absolute value here only because I know that the x has to be positive, or else the square root would not be defined. So both in the original and in the final, x has to be strictly positive. Ln of x will not be defined when x is 0, and neither will this up here. And I just showed you how we could check it by doing a derivative. We can also check it by doing a derivative on the calculator, basically. So what we do here is we put in y1 is our answer right here. So it ran off the screen here, but put that there for the y1. y2 is always the derivative of y1 with respect to x at x. And y3 is the original function here, the original integrand. And y2 and y3, the tables should match, which you see that they do here. Okay, so we have the entire family of antiderivatives. If we wanted to find a specific one, we would need a particular point on this curve, and then we could solve for the specific c. How can we use an antiderivative to evaluate a definite integral? Well, to do this exactly, I've got it down here below. Let's go down a little bit. Here it is. We want to come up with a family of antiderivatives. Take any one of those antiderivatives that we came up with, like the one with c is 0, which is one we usually pick. Put that in here, and then evaluate from 1 to 4. That is, plug in the top number, plug in the bottom number, evaluate, and subtract. So let's see if we can clean this up a little bit. 4 to the 6 times 2 is 8,192. And I can leave that like it is for the moment. Square root of 4 is 2 times negative 4 is negative 8. 7 times 4 is 28. Now I'm going to distribute the minus here. 1 to the 6 is 1 times 2/3 is 2/3. That minus makes it minus 2/3. Ln of 1 is 0, so this term is 0. Square root of 1 is 1 times negative 4 is negative 4, but that negative there makes it a positive 4. 1 times 7 is 7, that negative makes it negative 7. Combine all the parts that don't have the logarithms with them, and the 4 minus 7 minus 2/3 plus 28 minus 8 plus that many thirds, it turns out to be, actually it works out kind of nicely at 2,747. Notice this 8192 doesn't reduce, but once we subtract the 2/3 from it, 8190 over 3 does reduce to, let's see what it reduced to, 2730, I guess. And then you add the rest of this together and it gets 2747 plus 6 ln of 4. We could have also written that as, that's fine like that, but we could do 2747. Log of 4 is log of 2 squares, so it's 2 log of 2, so we could have said plus 12 ln of 2. That's another way we could have written that. And then if we put it in the calculator to approximate it, we get that number there, 2,755.31776617. Round off to whatever they ask you to round it off to. And of course we can get that decimal approximation without doing it exactly by just doing a integration in the calculator. It looks like this. In the older calculator, it would look like function integrate, and then you'd say, well, I've got my formula in y3, so I'd say y3 with respect to x, and then go 1 to 4. So either way, this is math 9 on the calculator. That's a TI-84 calculator. The next one, I have a definite integral and I want to evaluate it exactly and approximately to 6 significant digits. If I only needed the decimal approximation, I could just type it in basically like it looks on the newer TI-84s, and it would give me a decimal approximation. But if I need an exact value, I need to use the fundamental theorem of calculus. To do that, I need to find an antiderivative. To do the antiderivative, I need to do a substitution here. So let u be the more complicated variable base that's to a constant power. So the derivative of that, I need to find to get du. So the derivative here, 3 times 2 is 6. Power goes down 1 to 2. Derivative of 1, 0. And then, of course, you always have the dx. So if I put the x square and the dx here, So the dx is here, the x squared is here, the 6 is balanced by 1/6 out front, and the rest of this here becomes the 2 times x to the third plus 1 to the negative 4 power. So this part becomes u to the negative 4th. All of this part here together becomes du. And then when I change my integration here, these values are assumed to be whatever this variable is right here at the end. Well, since the variable is now u, it would be incorrect to say 0 to 2 because it would be u values, but I can fix that by specifying that those are actually x values there. Now, an antiderivative is pretty easy to come by here because this is just the power rule now that we made our substitution. So the power, whoops, let's go back up. So the power goes up 1, so negative 4 plus 1 is negative 3, multiplied by the reciprocal of that, which is negative 1/3. Multiplying these together, we get negative 1 over 18, and we can write u to the negative third as 1 over u cubed. Switch it back to let u be 2x cubed plus 1, and we've got this expression here. So there's an antiderivative. Of course, any constant added to that would also be an antiderivative. Now to evaluate, we take this thing, I'm going to factor out the negative 1/18 and bring it all the way out front. So then I just have this other part right here evaluated at 2 and at 0. So where the x is, put in a 2, and then plug in a 0, and then subtract. So let's see if we can clean this up a little bit. Let me start here. 2 cubed is 8, times 2 is 16, plus 1 is 17, so it's 1 over 17 cubed. 0 cubed is 0, times 2 is 0, plus 1 is 1, 1 to the third is 1, 1 over 1 is 1. So we got 1 over 17 cubed minus 1. I can multiply top and bottom by 17 cubed and turn 1 into 17 cubed over 17 cubed. So I get this here, common denominator, and I would distribute the negative 1 and get 17 cubed minus 1. The bottom is 18 is 2 times 3 squared, so the denominator is 2 times 3 squared times 17 cubed. 17 cubed minus 1 is 4,912, which actually I can cancel out a 2 out of this. And this one does not have 3 or 17 as a factor. It does have some other factors, but not those two particular ones. So this fraction is reduced. Go ahead and multiply out the bottom here, and we end up with 2,456 over 44,217, or approximately 0.0555442. So there was the exact and approximate values. We could check the approximate value by doing the integration with the calculator. Next, number 5. The population of a region is consistently growing at 5% per year. At the beginning of 2000, the population was 5.2 million. So it's growing, so it's a positive rate of growth. We'll call that R, positive 0.05, put it in decimal form. And we know that this is a exponential growth. Exponential growth, the population then is our initial population times 1 plus R to the t power. Well, let's see. R is 0.05, so this is 1.05. The initial population is 5.2, measuring p in millions of people. So we see that each year we're multiplying by 1.05, which means we're going up by 5% each year. The 1 is essentially our original, what we had, and the 0.05 part is our growth part. So this is how an exponential function works. One thing you should definitely know about exponential functions is that they are functions with a constant percentage rate of growth. So, moving on here, this is our formula. What's the population at the beginning of 2008? Now let's see, t is 0 at 2000 at the beginning. So the beginning of 2008, t equals 8. So it's just p of 8. So you take this and plug in 8 here, work that out on your calculator. It's about 7.68 million people. What's the average population for the first decade of that millennium? So from 0 to 10, Okay, that's our interval. And our p average is 1 over b minus a times the integral. So it's 5.2 times 1.05 to the t, going from 0 to 10. Since I just need a decimal approximation, I can do that this way. I could also work this out pretty easily as a actually find an antiderivative. The antiderivative is pretty easy, 1.05 to the 10th, and then divide by a log of 1.05, and then just evaluate from 0 to 10. And either way, you're going to get approximately 6.70 million people. I think technically this may be off a little bit. Technically, the millennium didn't actually start till 2001. So the first millennium really would go from 2001 to 11. So just maybe should more properly be the integral from 1 to 11. Otherwise, it would work the same way. What's the total area in the first quadrant bounded by the following curves? So we need to graph these curves and then work this out. So the first thing we're going to do is we're going to graph this. And so here we have the graph. This one here, this vertical y equals, or x equals 0 is the y-axis. This is y is the exponential. What is it? E to the, let's see what we've got here. 2 to the x. And this is 8 minus x squared is y. Is that one there. So we see, if we graph these, we see that we have this shaded region is what's actually in the first quadrant that has these three curves. As it's the finite region in this first quadrant that's bounded by these three curves. Now, we need to find the x values on the ends. Now, the left end is pretty easy. It's 0. It's back where we can see it here. Whoa. We do, however, want to see the this other point where they intersect. And this other point where they intersect, we're looking at solving this system of equations where we're seeing where y equals 2 to the x equals 8 minus x. And it looks like it might be 2, and in fact it really is. 8 minus 2 squared is 8 minus 4 is 4. And 2 to the second is also 4. So in fact, that point is the point 2, 4, is that point right there, our point of intersection. So our x's are running from 0 to 2. And if we look at this, if we had a typical little strip, it would run like this, little rectangle, very small width, delta x, and the height is this quadratic minus this exponential. So we take all those and add them up, take a limit, we have now an integral. So what are we integrating? We're integrating top curve minus bottom curve. So if we saw from the graph, the top curve was 8 minus x squared, the bottom curve was 2 to the x. And our x limits were from 0 to 2. And so there's our integral. This is 8 times the integral antiderivative of dx. This is minus the antiderivative of x squared minus the antiderivative of 2 to the x from 0 to 2. Then antiderivative is x. This is 1/3 x cubed. This is 2 to the x times 1 over log of 2. Evaluate from 0 to 2. Plug in 2 here and 0 here. Let's start with the 0 part. 2 to the 0 is 1, so this is minus ln of 2. This is 0, this is 0, and that minus makes that plus 1 over ln of 2. And over here we get minus 4 over ln of 2. Negative 4 over ln of 2 plus 1 over ln of 2 is negative 3 ln of 2. 2 to the third is 8, so this is 8, this is negative 8/3. 16 minus 8/3, get a common denominator, that's 40/3. So this is the exact value right here, 40/3 minus 3 over natural log of 2, or approximately 9 9.00525. And that's the area there shaded that we're looking for. Next one is a probability situation for a continuous probability. Okay, so the probability density function, PDF, for duration of telephone calls is given by this formula here. Sketch the graph of the density function over appropriate domain. Well, the appropriate domain for this is the length of a call, so the call has to be a positive length. So this only works from 0 to infinity. You might say the PDF is defined for negatives as just being 0. So, or in other words, we can ignore stuff over there. So, here is what the graph looks like. A little trial and error perhaps to find the right grid range, but we certainly know it's a first quadrant graph. Now, the first question is, why is this, how do we know this is a legitimate PDF? Okay, well, there are two conditions that must be satisfied. The y values of PDF of x must be greater than or equal to 0. Well, e to the any power is positive times 0.3 is still positive, so it's clearly positive. It's not even equal to 0 on its anywhere it's defined. And so then the other thing is the total area underneath the curve must be 1. Now this is going to require us to compute an integral, technically speaking, from negative infinity to infinity, but we're just integrating 0 from negative infinity to 0, so that part doesn't matter. So we're just going from 0 to infinity, our PDF there. And to do this, we let u be negative 0.3x, du is negative 0.3 dx. So if we put the 0.03 over here with the dx, stick in a negative here, which is balanced by the negative here, then this part in parentheses becomes du, and this part right here becomes e to the u. And we still have our minus up front. So, this is evaluated from 0 to infinity, and that means you take the limit as x goes to infinity here. So, that's minus e to the u is the antiderivative, that's minus here. So it's the limit as x goes to, whoops, let's see if we can fix that. That infinity, what that means is the limit as x goes to, this infinity there is supposed to be down there. Okay, and then you plug in 0 here. So 0 here makes e to the 0, which is 1. Those two negatives makes plus 1. This limit here goes to 0. The bigger x gets, the more negative, the further into the negatives this power gets. And so the smaller this whole thing gets, closer and closer to 0. So that limit is 0, add 1 is 1, and that satisfies the second condition, which we had to show. Now if you try to do this with your calculator, you can do it. However, what do you have to do? You have to plug in some value for infinity. Here I plugged in 100, and we saw that that integral seemed to be 1, or at least to the limits of the calculator. Now, you can't really plug in 100. You can plug in 100, you can't really plug in infinity in a TI-84 calculator. So what this means is, even though this gives us some pretty good idea right here that that actual integral is 1, you have to do this calculation on the left to be 100% sure. What percentage of calls last between 2 and 3 minutes? That the probability that x is between 2 and 3 is the integral from 2 to 3 of that PDF. Okay, and again, you can see me working out the details, the same process of finding the same antiderivative. I could have skipped down to here since I already knew the antiderivative. Plug in 3 and 2, and we get this expression, e to the negative 0.6 minus e to the negative 0.9, and that works out to be about 14.224. If we look at the graph, that's illustrated by this area that you see here between 2 and 3 on the graph underneath the PDF curve. So it's that area there. And of course that's given by this integral. Here I did it with the calculator using Math 9 function integrate using, this is the older calculator, it looks like that. The newer one would look just like this over here, like we write it. So probabilities are areas under the PDF graph. To find the mean, okay, we want to take the x times the PDF and integrate that. And so I did that here. This requires integration by parts. So we put a negative with this part here and this part. Put a negative with both parts. So we multiply these together. We're back where we started. Think of this negative x as being u. Then du is just negative dx. Then here dv is the rest of it, which is e to the negative 0.3x times negative 0.3 dx. And that just becomes e to the w dw if you let w be negative 0.3x. So the antiderivative of that is e to the w, or e to the negative 0.3x. So what we have here with the substitution is the antiderivative of u to the v, u dv. First of all, notice it's an improper integral, so that means you're putting a b up here, taking the limit as b goes to infinity. Now we're taking that and doing an antiderivative and then evaluating from 0 to b and then take the limit. So that's the integral of u dv according to the parts rule, which is the product rule backwards. That's uv minus the integral of v to u. And so u times v, if we look back up here where we can see it, here's, so you're multiplying these two things here. Here's u and v, multiply those together, that's right here. And then we multiply these two together to do the second integral, v du, and that's right here. Again, we stick in a negative stick in a 0.3 and a 1 over 0.3 out front, and then this becomes e to the w dw with that same w, negative 0.3x. And so we get e to the w there. 1 over 0.3 is 3/10. The reciprocal of that is 10/3. So 1 over 0.3 is 10/3. Still negative out front. This negative is built in. Was the negative from here, and that's dw, so you get e to the w. Going from x to b, x equals 0 to x equals b, e to the w is negative 0.3. Now we plug in the b for x and the 0 for x. Actually, I factored out the e to the power first, and then I plugged in the b and the 0 and subtract. Now let's do the 0 part. Let's see. 0, negative 0, 0 minus 10/3, so it's negative 10/3. That negative makes positive 10/3. This is e to the 0, which is 1 times the 10/3 is 10/3. This I could rewrite as negative b minus 10/3 over e to the negative, or over e to the positive 3 to b. And it turns out as b goes to infinity, this bottom is growing much faster than the top, so this fraction approaches 0. To do this formally, you could use something like L'Hopital's rule and work this out. But anyway, that limit is 0, and you add 10/3, so we see that the mean, or average length of a call, is 10/3 minute, or 3 1/3, 3.3 repeated minutes per call. What's a cumulative density function? CDF. CDF is a specific antiderivative of the original PDF function. It's from wherever the function starts, which in this case is 0, well, negative infinity really up to x, but negative infinity up to 0, we're integrating 0, which is nothing. So this function really starts at 0. So we're going from 0 to x, and this is the PDF evaluated at t. Again, it's the same substitution that we did before, same antiderivative. It is e to the u minus e to the u, but we're evaluating it from 0 to x, so we plug in x here and 0 here. When the dust settles, this is e to the 0, which is 1, those two negatives make positive 1, and then minus e to the negative 0.3x. So there is the CDF graph. Of course, we could graph that. We should see it starting at 0 on the left, going up to 1 at the right, be continuous and increasing. The median of a distribution is an x value, so that the cumulative probability, that is the probability to the left, is 0, or is a half. You can do this sort of thing for any probability, anytime you know the probability to the left. Like if if you wanted to find the first quartile, then we know the probability to the left is 0.25. If we want to find the 80th percentile, we know the probability to the left is 0.8. The median, we know the probability to the left is 0.5 or 1/2. So we know 1/2 is the probability that x is less than or equal to median m. And so that is, if we integrate from 0 to m, the PDF, we get 1/2. So we can look at it that way. Or, of course, if we know the CDF function, it's just CDF of 1/2. CDF of m equals 1/2. Touchy, let me get back to where I was. Here we go. So it's just CDF. You really need to get your hands on the CDF, basically, and solve this. So since we have a formula for the CDF, we can do that. So CDF of m is 0.5. Well, CDF of m is 1 minus e to the negative 0.3 times m. That's 1/2. Just solve that by subtracting 1, dividing by negative 1, taking the logarithm of both sides, and then dividing by negative 0.3. So m is natural log of 0.5, or 1/2, divided by negative 0.3. 1/2 can be written as 2 to the negative 1, and that becomes log of 2 to the negative 1, which is negative log of 2 of just 2, and the two negatives cancel. And the reciprocal of 3/10 is 10/3, so that one could be written as 10/3, excuse me, times natural log of 2. That would be the way I'd prefer to write it as an exact value, although this natural log of 0.5 or negative 0.3 is really just as good, I guess. And that's approximately 2.31049. So the median and the mean are both measures of the center of this distribution. Mean is the average, and the median is the place where half of the probability is below it. Now we can do this on a calculator without getting our hands on the actual CDF. This way, we type in our formula for our antiderivative and our 0.5, and we see where they cross. Or we could type in our PDF and have it numerically do a definite integral up to a variable x, and to get at least approximately get the CDF, and then again find out where those two cross. So here's a graph of the CDF going from 0 up to 1, and actually starts at 0, but then it comes up and levels off with an asymptote at 1. And here's the y equals 0.5. Calculate the intersection. Of course, numerically, that's the same as that thing that we have here. So half of all the calls are less than 2.31 minutes per call. When the brakes are fully applied, a certain automobile has a constant deceleration. Now notice it's deceleration, so that makes the acceleration negative. And it has initial velocity of 90 miles per hour. Now we got a problem here because our units aren't matching up. We got miles per hour here, we got feet per second square here. We need distances in either feet or miles, one but not both, and we need time in either hours or seconds but not both. So one of the first things we're going to do is make a conversion. One of these two we're going to have to convert. So what's the formula for the velocity of the automobile as a function of time from the time the brakes are applied till it stops? What's the formula for the position? How long did it take the car to stop? And how many feet did it travel? Well, again, like I said, the first thing we want to do is to either make this all in feet and seconds or all in miles and hours. I chose to make it feet and seconds. So notice 90 miles per 1 hour. That's what we start with. Well, we multiply that by 5,280 feet, which is in 1 mile. So multiply that fraction. Notice the miles cancel. 1 hour over 60 minutes, 1 minute over 60 seconds will, this time the minutes and the hours will cancel, and when all the units cancel out, we're left with feet per second. Multiply all the numbers in the top, divide by all the numbers in the bottom, you get 132 feet per second. So if you take the motion of the direction the car is pointed, where it's starting moving is positive, then acceleration is negative, so it's because it's in the opposite direction, because it's decelerating, slowing down. So the acceleration, whoops, go back here. Okay, so acceleration was this negative value. Get back to where my screen I want. Here we go. Almost there. Okay, so here we go. The velocity is an antiderivative of the acceleration because the derivative of the velocity is the acceleration. So it's for a particular constant value. So since the acceleration is a constant at negative 23, and that is feet per second square, the velocity will be negative 23 times t plus some constant 1. Okay, velocity at 0 is 132 miles per hour in the positive direction, 132 feet per second, in the positive direction. So we plug that in for v, and this will allow us to solve, and 0 for t, and that will allow us to solve for c1, and c1 actually is 132 then. So velocity is negative 23t plus 132. Notice we take the derivative of that, we get negative 23, which is the acceleration. Now the position, which I want to use the letter S for, it's kind of traditional to do that, would be then a specific antiderivative of the velocity. So if we take another antiderivative, now we're going to get a quadratic equation, quadratic formula for the polynomial there, for that function. So the power goes up to second power, and we divide by the new power, so that's negative 23 halves t squared. The constant term picks up a t, and then we add a constant 2. So again, if you take the derivative of that, you get the velocity. And the second derivative then would be the original acceleration. We're starting at a position, if we just call the position we started putting the brakes on position 0, then the S of 0 equals 0, and that allows us to solve for C2, which is 0. So our position is negative 23 halves t squared plus 132 t. Now at some point the car will eventually come to a stop, and for this value we see the velocity is 0. So negative 23t plus 132 equals 0. We can solve that for t by adding 23t to both sides and dividing by 23. So t equals 132 over 23 seconds, or 5.739 etc. seconds. Now at this time the position is S of 132 over 23 I should have said, and plug that into the formula for S. Okay, remember S up here was what? It was negative 23t plus 132. So that's negative 23, there it is again. Negative 23, and t is 132 over 23, then we square it, plus 132. Okay. That shouldn't... Wait a minute. Something... Yes. Let's go up here. I was looking at the wrong formula. Yeah, here's S. Negative 23 halves t squared plus 132t. So that's correct. We plug in 132 over 23 for t in both those places. Work that out. There it is in fraction form, or approximately 378.78 feet. So, and how long is it going to take that? We saw that time up here. So we solve for that time first, and then we plug it in to find the position at that point. And since we started at position 0, this is going to be how far it took us to stop, how far it skid or whatever. So it's going to take it 5.74 seconds to come to a full stop, and it will go about 379 feet before it stops under these conditions. Let's come back in the next video and finish up the rest of these problems in that video.